Okay, hello everyone. I hope you had a great lunch. So I'll be talking about conformal symmetry in field theories in this lecture series. So I hope to talk about why we should consider conformal theories and what exactly is conformal symmetry and how can we use that symmetry to put constraints in field theories, quantum classical, and the recent program of conformal bootstrap, which has been around, which has flourished in the past 2 decades, and the developments in this program in the last few years. Now, I really don't think I will be able to cover all this. I probably will only be able to cover like first few items, but this is the ambitious goal. But among all this, out of this, the most important for me is the first one. Why conformal symmetry? Why should we consider conformal symmetry? Why should we try to learn conformal symmetry? Like this, my ultimate goal at the end of this summer school, if some of you, ideally most of you, agree that conformal symmetry is important, if I can convince you guys to that, then I will consider myself successful. So that's my ultimate goal, to motivate why we should consider conformal symmetry. Now, conformal symmetry is mentioned in literature in abundance, but high energy theorists or physicists in this area in general mostly think of conformal symmetry in 2 dimensions, right? Because like in formal mathematical physics, let's say, mathematical physics, like in string theory, M theory, no, it's generalization, or like supergravity, in stuff like that, the conformal field theory that's mentioned is always like 2D CFTs, 2-dimensional CFTs. And you can see like there are lots of books about 2D CFTs. Actually, 2 of them happen to be written or edited in Istanbul. You can find them in my references. I'll talk about that later. But there are lots of books about 2D CFTs, lots of discussion, a huge literature. Now, they are really important. There's no argument here. They are useful in string theory and blah, blah, blah. However, the main reason, and this may be my personal opinion, the main reason we always talk about 2D CFTs is not because they are more important than CFTs in higher dimensions, like, CFT D, with D being 3, 4, etc. It's not like 2D CFTs are more important, but rather because we know how to solve 2D CFTs mostly. Like it's a lot easier to have control over 2D CFTs, which is why we always talk about 2D CFTs and kind of ignore CFTs in higher dimensions. If you look at the literature, this is the case up until last few decades, because we know how to solve them and just we write articles about them. However, CFTs in higher dimensions are actually very important. And well, if you were to ask, it depends on who you are asking. For me, for example, they are more important. And they have lots of applications, like they have applications in cosmology. If you are doing cosmology with an inflation model, there is a time in the history of the universe where Hubble parameter is almost constant. And during that time, the FRW metric becomes a de Sitter metric in the conformal time. And the de Sitter metric has a CFT at its boundary. So if you are studying cosmology, CFTs are relevant for you. If you are doing material science, like if you're analyzing polymers in some solutions and their behavior for their formation, etc., in some cases, you need to know CFTs to explain these materials. Or if you are doing, let's say, solid state physics, like if you're analyzing superconductivity at around some phase transition, supercritical fluids, you need to know conformal field theories. Or if you are doing standard QFT, then we know that some gauge theories have conformal windows for some particular number of flavor numbers. So just take any gauge theory and you can flow to a so-called Banks-Zaks fixed point. And at that point, we know that CFT governs the behavior. So for ordinary gauge theory, CFTs are relevant as well. And the list goes on. And these are all higher dimensional CFTs. So in these notes, I will be talking about higher dimensional CFTs, but not 2D CFTs, okay? Because I think 2D CFTs are already very covered, and one needs to analyze them separately because in 2D CFT, the relevant symmetry actually enlarges. It becomes Virasoro symmetry. So it becomes Virasoro. So you need to analyze them separately. And in these notes, as I said, I will be working with higher dimensional CFTs. And my ultimate goal is that by the end of this week, I will convince most of you that we need to know higher dimensional CFTs for most practical purposes. Okay, so this is my ultimate goal. Now, so in this talk, like my target audience is, I will try to make it so that it is as dispersed as possible. Okay, so I will assume that the participants does not know general quantum field theory, how to work with them. The participant doesn't know RG formalism, you know, renormalization group, fixed point, etc. I will assume that you don't know like semi-advanced topics like critical phenomena, lambda formalism, etc. And in general, I will assume you don't know like conformal algebra, harmonic analysis in the conformal group. And also, lastly, I will assume you do not know subtleties with Lorentzi signature, such as like distribution nature of wave functions and so on. So I will assume that I will try to introduce these concepts. So that means for participants who already know this stuff, some of my talk will be trivial. And maybe all of my talk will be trivial if you already know this very well. So it will be trivial for you. But nevertheless, to make sure that at least almost everyone can follow the talk, I will make it so that you do not need to know anything about this. I will try to introduce them. And again, I apologize to advanced participants and please bear with me. Now, as I said, the lectures will be semi-self-contained in the sense that I will be talking about these RG flow, critical phenomena, etc. But the fully self-contained one will be the lecture notes, which I am already writing. Okay, so you can find lecture notes in the Slack channel. If you haven't already joined, there is a Slack channel, and I already put my notes there. You can. It's in GitHub. It's in GitHub. I put the link to the Slack channel, so you can check the notes there. Okay. And of course, you are very welcome to initiate discussions, ask questions to me, to each other, etc. in the channel. More the merrier. I mean, it's better if we engage, so it can be more efficient. Now, during the talks, I will not bother citing any sources, okay? But I put all the sources in my notes, so this is my disclaimer. And as I said, I will be talking about higher dimensional CFTs, so I already mentioned that. Okay, so, oops. All right, there we go. Okay, so I would, for today, and maybe tomorrow as well, I will go through the notes. And as I said, I will be mostly focused on motivating conformal field theories today, and maybe possibly tomorrow as well. And I will do that by discussing some stuff in statistical physics, in cosmology, in other areas, etc. And I will step by step show you where conformal field theories emerge and why we need to know about these symmetries. Okay, so I will be going through these notes. Right now, the notes are really, really incomplete. Like I only finished like chapter 1 so far. I will be talking, I hope to like gather lots of stuff here. Hopefully it will be useful. And I'm writing these notes to a grad student in Turkey, at least my image of a grad student in Turkey. Like I also did my master's in Metro in Turkey. Like I have like a rough idea of which courses are opened in Turkey, which ones are not. So I am trying to write these notes for the level of, let's say, first year PhD student in Turkey. So hopefully this will be helpful. Okay, you can follow them in GitHub. And as I said, I put some literature recommendation here. Now there are some books. I put some books here, some lecture notes, some reviews, some Tazi lectures, for example. I put lots of sources here, you can check them. There's also like an active blog by Slava Richkov, Bootstrapper. You can check that site as well. I put some link to some YouTube channels of containing videos of some summer schools related to conformal field theories and conformal bootstrap program. In particular, like there's this 2017 and 2018 bootstrap school videos in YouTube. They are really introductory and pedagogical, because I feel like the most important thing here is being pedagogical and introductory. Because if you already know like very well quantum field theory and RG formalism and curved space, etc., if you already know them very well, the understanding CFT is kind of straightforward. You can just open up any introductory lecture note and do it yourself. So the videos, in a sense, should summarize these points for someone who don't really know these details. In that sense, these videos are really helpful. And yeah, I put these two sources, the strings and symmetries in 1994 and conformal field theory in 1998. So these are like edited by Güven Aktaş, Cihan Saçlıoğlu, Meral Serdaroğlu, and Yavuz Nutku, Cihan Saçlıoğlu, and Teoman Turgut. So these two books, published in 1994 and 1998, are collections of seminars about string theory and conformal field theories done in Istanbul, in Boğaziçi University. At that time, actually, it says, it is done as a memorial of Reza Gürsey, who worked in conformal field theories back at, in his time. Yeah, he really worked a lot about conformal field theories, and to honor his, as a memorial, there was these seminars and conferences, and the collections were published as books. So these are not related to what we were doing, because these are 2D CFTs, but I wanted to cite them for sentimental reasons. Okay, good. Are there any questions before we start? Is there any question? Anything not clear? Please disturb me, just interrupt me. If you have any question, don't wait till the end. Do not write in chat, I may not see that. Just unmute yourself, ask your question, okay? If there's not something lengthy, I would be happy to chat and discuss it at that time. If it is something lengthy, we can always talk about it later, okay? But just ask your questions. It's more helpful if we interact. Okay, good. So let's start. I will start with something very, very, very simple. I will start with phase diagrams, okay? So, well, we all know that from elementary school or kindergarten, that matter has different phases, right? For fluids, we have three main phases. We have gaseous, liquid, and solid. And conveniently, we put them in so-called phase diagram, right? So this is the phase diagram. This is called phase diagram. It has temperature in this axis and pressure as its axis, and we denote different phases depending on these values. Okay, so this is something we all know. And in this phase axis, there are some regions. Let's say this is like the region where the matter is, the fluid is in gaseous form, and there are some lines, like this line, that is the evaporation line, right? There's a transition between liquid to gas in that line, and there's this line. And there's something less known, less commonly known. Oops. Yeah, okay, there we go. And there's something less known, which is the critical point. So this transition ends at this point. So what does that mean? What is the transition? How do we interpret phase lines? And we will come to that. And likewise, we can have a phase diagram for uniaxial magnets. Now, uniaxial magnet is idealization. It considers magnets as a lattice site with bunch of spins, and each spins, let's say spins like this. Okay, there's a lattice site and there are spins at each point. Let's say these are lattice sites, and there are spins at each point, and spins are pointing either up or down. So it's one-dimensional magnet, okay? That's called uniaxial magnets. And let's take these magnets, and this is its microscopic description. And this magnet has some phases as well. And we describe these phases of these magnets as a phase diagram as well. This time, we have two axes like fluids. We again have temperature, but instead of pressure, we have the external magnetic field. Okay, because if we have like external magnetic field, let's say like this, these spins will try to align with that field. So, which is why external magnetic field determines the behavior of magnets as different phases. Okay, so, okay, we started with this very simple, I think, a phase diagram. And we know that microscopically, we can distinguish different phases by phenomenological parameters. For instance, we can say solids are high viscosity and low compressibility, liquids have low viscosity and low compressibility, and so on. Here, this thing called viscosity or compressibility are not microscopic properties, right? If we were to write down a Hamiltonian for, let's say, water, water is the fluid, right? Water is the fluid. It has phases, solid, like ice or liquid, etc. But if we were to write a Hamiltonian for that, we wouldn't have viscosity or compressibility. These are emergent phenomenological parameters. I will come to this later, like why phenomenological models are important. Okay. Now, these two phase diagrams are two-dimensional, right? We have two axes, but this doesn't have to be like this. In general, we can have like higher dimensional phase diagrams as well. For instance, this is the phase diagram of a tissue. It's like a biological problem. In a biological problem, they are trying to examine the surface instabilities on biological tissues. Okay, so they analyze it as they model it as a statistical mechanical problem, and they determine the phase diagram. Now you can find the resources. Anyway, and in this phase diagram, we have three axes, and we have multiple phases in these three axes, right? So this is possible in general. If you give me any model, I can try to find this phase diagram. I can find different phases. Now we can try to do this for water as well. Earlier we said water has two axes, right? Temperature and pressure. Now I can say, okay, let me also consider the molar density. Let me write it here, like molar density V as the third parameter. So now this is like the phase diagram of water with three axes. You see like this part, the pink diagram here, the projection into temperature, pressure surface, and it is just like what we saw earlier. We can do that, there is no problem. And this is like a schematic form as a contour diagram. It is fine. But the thing is, we do not need to do this. We can go to all of the phases of water or any fluids, or actually most fluids, by just considering two parameters, right? I can change temperature and pressure to go to liquid phase, liquid phase, gaseous phase, or solid phase without changing a third parameter. So we can say that we at most need two parameters for fluids, so the diagram is two-dimensional. Now, it's not really actually very important, the global property of the diagram, like how many dimensions it is, but what will be important, like how many dimensions we need, will be important for certain points in the diagram, so-called fixed points of renormalization group flow. Now, I will review this later. Right now I'm assuming you do not know renormalization group flow. I'm assuming that it's a very useful technique introduced in the 1970s and 80s in statistical mechanics, and right now it's used in statistical mechanics and high energy theory. Basically, it's like a very modern way to look at things, but I will assume you do not know it, so I will review it. Okay, but as I said, we can say that the fluids have phase diagram two-dimensional because we only need to tune two parameters. Okay, how many parameters we need to tune to go to a point in the phase diagram is important. That will be important within the renormalization group formalism. And that can be applied to anything. Like, for example, you can have the phase diagram of QCD. I will actually show that. There's a phase diagram for the QCD, quantum chromodynamics. And in that phase diagram, there will be like lines like this, there will be points, critical points, and you will be tuning baryon chemical potential, and temperature or the energy scale to go from point to point. So this phase diagram thing is not just true for fluid or magnet. You can use it for QCD as well. Like, it's a general thing. And as I showed you, like, people use it for biological tissues. Okay. So that's something generic. Now, is there any questions so far? Okay, good. Now, okay, let's take a step back. Like, okay, I am trying to motivate conformal field theories, right? Good. But I started with these phase diagrams. The connection is not clear so far. But let's try to understand phase diagrams first, because that will prove useful later. Now, in the phase diagram, we have some bulk phases, right? There are regions, let's say liquid region, solid region, etc. There are some lines that divide those regions, and we call them phase transitions. Here, like this is a region, these are regions, right? And there's this line that divides two regions, and we have so-called phase transition through that region, okay? But what are these phase transitions? How do we interpret them? And what about the endpoints of these phase transitions? We usually call them critical points. How about them? I mean, how do we interpret them? Now, from statistical mechanical point of view, the phase diagram actually consists of non-analysis of the free energy in thermodynamic limits. So you may or may not remember it. So we have this formula for free energy. Now, F is, I'm not sure how much you remember from your statistical mechanics course, but this is free energy. It can be like Gibbs free energy, Helmholtz free energy, Landau free energy, and so on. We don't bother which one it is. This beta is inverse temperature, 1 over Kb times T. Kb is the Boltzmann constant. And H is the Hamiltonian, which includes all interactions that are relevant. And here trace means we are integrating or we are summing over all degrees of freedom mentioned in Hamiltonian, okay? So if I consider e to the minus beta h and sum over all degrees of freedom mentioned in the Hamiltonian, then that gives me so-called partition function, and the partition function is related to free energy as z is equal to e to the minus beta times f. Okay, and f is the free energy. Now, what is this free energy? If you don't remember, it's like the ultimate function in statistical mechanics. If you have the free energy, you take its derivatives to compute stuff. Like you can compute susceptibility, you can compute compressibility, you can compute the expectation value of the order parameter, like anything basic, or heat capacity. Like if you need anything, if you need to compute anything, you just use free energy and take its derivatives. Okay.
Can I ask a question here?
Please.
The Hamiltonian is an operator, but is the free energy a function, or it's a, because I think it can't be an operator.
Right now, this is a classical thing. So H is not operator. It's just a function. Okay. So just as classical statistical mechanics. Yeah. And even if we move on to quantum field theory, for example, we will have basically the same thing, and Z will be vacuum generating function, and actually this trace e to the minus beta h will be like path integral e to the minus, let's say, action s, right? Instead of beta h, we will have action. This action will still be a C number within the path integral. Okay, so it will not be anything different. Anyway, but for now, let's stick on quantum,
Okay, thank you.
Statistical mechanics. Good. Okay, I'm having hard. Okay, now, there we go. Good. Another question? No, okay. So long story short, if I know the Hamiltonian, then I can just write e to the minus beta h, take its trace, and that gives me the partition function. From that, I can get the free energy, and free energy gives me the phase diagram. And any non-analyticity in the free energy, like if you cannot take its derivative at some point, if there's like a non-analyticity, then that gives you the position of the phase diagram. So for instance, if you write down there we go. So for this phase diagram, let me just clear everything. Okay, for this phase diagram, we just need to write down the Hamiltonian of the fluid, let's say water, right? And then that means there are some non-analytic regions like this region, this line, the free energy is not analytic. because there's a phase transition. Likewise here, it's not analytic at this critical point. But how non-analytic? And can we really see this, like how to get this phase diagram? And that's what we will move on now. Good. So that's good. The thing is though, I cannot actually compute this thing. Like, okay, it's good. We say, right, this is the general formula. We have it, great. Statistical mechanics tell us that if you use this formula, then you can compute the free energy and everything. But the thing is, this thing in general cannot be computed. Now, there are like two things at play here. One thing is it's very hard because the number of degrees of freedom is huge. Let's say you have 1 million atoms or 1 million molecules, right? This trace means you need to sum over the possible motion of 1 billion or million molecules. That's not feasible. That's the first thing. And second thing is that this problem itself actually undecidable. Like in mathematical, something is called undecidable if it is not guaranteed to find an algorithm to solve that problem in finite time. So it was shown, I think it was 2 years ago or 4 years ago. It was shown in 2D case, not general case, but shown that this problem is itself, like getting the phase diagram from microscopic theory, is mathematically an undecidable problem. It's just like finding a Turing machine. So there is no machine, no algorithm that can give us this result generically. Anyway, the relevant article is here. So long story short, even though we have the physics, we cannot really use it. So what can we do? Well, we can write down a phenomenological model for the free energy. Now, when I say phenomenological, I use it in a particular sense, and I do actually explain it here. Like I cite, like there's a very nice explanation of this from an old book called Fandel, explains it, but I will not be going over it now. So when I say phenomenological, basically what I'm saying is that we are not considering the macroscopic details, but we are working with macroscopic variables. Like instead of using this macroscopic formula, I will be introducing this formula where now this phi is a continuous field. It's not continuous. Now we know that, for example, for the case of fluids, let's say water, you cannot describe things with a continuous field because it's a discrete thing. Like there are discrete water molecules. But starting with the discrete water molecules, it's almost impossible to compute free energy. So what I'm doing is that I'm introducing a density field, let's say rho x, which gives me the average density of the water molecules at point x. Okay, oops, sorry. So rho x, for example, or actually in this case, it will be like phi x. So I'm introducing some continuous field which kind of captures the physics at the macroscopic details. And this is what I mean by phenomenology. Okay. And now I am doing a path integral over it. If you don't know path integral, it's fine. I do not require knowledge of path integrals in these notes. Okay. Just think of this as not ordinary integral. It's fine. Okay. Now it's almost the same thing. Now instead of Hamiltonian, I have this function L, Ki, phi. Phi is my continuous field. It captures degrees of freedom. I'm integrating over them. And Ki are some phenomenological constants like viscosity, compressibility, etc. Okay, they do not exist in the macroscopic theory, but I can write them like that. So far, so good. Now, let's try to do this integration. Now, we cannot do this in general. Okay, so mathematically, we do not know how to do path integrals for general functions. That's another problem, but I will not go into that. But I can assume that if this L is very large, actually, maybe I shouldn't. Okay, let me show it like this. If this L is very large, very, very large, then this is almost zero, right? This thing is almost zero, except at the minimum of L. Like let's say L is like a function like this, okay? So the major contribution will come from its minima. And I can approximate this integration as like approximately e to the minus beta L Ki phi bar, where phi bar is the value of the function phi, which minimizes this function L. Okay, so I can do that. This is called saddle point. Well, it's not actually saddle. It's actually Like it's like the saddle point approximation. Point, not exactly, but approximation. Not exactly. Actually, this thing is called mean field theory approximation. Mean field theory, because physically, I am saying, okay, this phi, the function phi, may fluctuate, but this contribution that will be coming through this integral will be negligible, and the main contribution of phi x will be when it's a constant phi bar, which minimizes this function. Does it make sense so far? Any question? Okay, so if I do that, then I get this expression. Great. That means the free energy is just this function L evaluated at its minimum. Okay. Let me summarize this. I introduced a microscopic variable phi, measurable, and this thing is called order parameter in statistical physics. And we write down an analytic function of L in terms of these phenomenological parameters Ki, like compressibility, etc. And this L should have the symmetries of the Hamiltonian, because I'm basically writing it instead of Hamiltonian. Okay. Then we minimize L with respect to phi and say that the minimum gives the free energy. And if there is a non-analyticity in taking the minimum, then that should give us the phase transition. Now, this approach is called Lambda formalism, name of the Russian physicist. Well, I think he's Russian, but at least he's from Soviet Union, but I think he was Russian. Lambda, and this L is called Lambda potential. Okay, so Lambda potential is simply an application of the mean field theory. We assume that whatever is physically interesting, like this order parameter phi, can be taken as its mean value, phi bar. So I'm approximating phi as phi bar and ignore the fluctuations. Okay, so this is Lambda formalism. Good. Now let's consider, by the way, these will be relevant in higher energy physics. Like, this is not just statistical physics. Like, this concept will actually, as you will show, basically the same things in quantum field theory as well. So just don't think of this as something irrelevant to your field of study, whatever it is. Okay, you may find this quite useful in your case as well. And these are, again, like, if you find this trivial, my sincere apologies, but I think I will presume that you may not be familiar with these concepts. Okay, so let's consider uniaxial magnets. So you remember we said the uniaxial magnets, which was basically, okay, so like this thing is like uniaxial magnets. There are a bunch of lattice sides, and each lattice side there's like a spin. It's either spin down or spin up. Okay, and so we are considering that thing. So okay, let's consider that, and let's write down the lambda potential. So this is like the simplest lambda potential. Okay, I have m squared, m to the 4, and m. Okay, like this. There's m squared, m to the 4, and m. Okay, I'm taking the simplest one. And there are like these phenomenological coupling constants, the phenomenological constants, K1, K2, etc. This H is external magnetic field. Okay, so there's this coupling. I'm choosing this minus. That actually refers to ferromagnetic coupling. If this was plus, it would be anti-ferromagnetic, because you see, you want to minimize lambda potential. That means if your magnet is ferromagnetic, the spins will try to align with the external magnetic field. So if H and M are both up, you want L to get minimized. So this is ferromagnetic. If this was plus, that will be anti-ferromagnetic. Not important, but anyway. And I'm truncating other terms like m to the 6, m to the 8, etc. Now, in general, you may ask why. Is it warranted? No, it's not. Like, I'm just kind of doing an approximation here. But I will later show that this is a valid thing to do, and actually it's self-consistent. Like, adding higher terms wouldn't change anything if this is applicable at all. Like, if the lambda formalism is applicable, then truncating it is fine. But in some situations, it's not applicable. Anyway, and this has to do with like renormalizability of the theory, actually, whether it's renormalizable or non-renormalizable. But anyway, let's forget that for now. Now, this K0 simply shifts the free energy, so we can discard it because anything physical is in the derivative of free energy. Okay, so I have constant wouldn't change anything physical. I can also scale m so that m to the 4 doesn't have any coefficient in it. So now this is lambda potential. I have two coefficients, a and minus h. Okay, now if I plot this, okay, let me first try to minimize it. Okay, this thing, because we said free energy is its minimum. Now, if we try to minimize it, now if a is greater than 0, then there is a minimum, which is this thing. And the value of m, which gives that minimum, is this. So magnetization becomes this thing, and free energy becomes this thing. Now, if a is less than 0, then magnetization can take two values, plus minus, and this is the minimum of free energy. So we observe that at the minimum of the, if a is less than 0, then we actually have a symmetry breaking. Actually, it's better to show this graphically. Okay, it's easy to understand like that. So this blue line is just a lambda potential. Okay, it was like am squared plus m to the 4 minus hm, right? That was lambda potential. And this black dot, it's minimum. Now, here's the thing. If h is not 0, like if h is less than 0 or more than 0, then as you change a, the minima moves continuously. No problem. You see, minima just goes to the right as you change a. However, if h is 0, and if we change a from positive to negative value, you actually get a symmetry breaking. So the minima changes continuously, but it needs to pick one of these two things. This is actually called continuous phase transition. Continuous phase transition. If we go like this, because the minima changes continuously, but it needs to pick one of these, so there's a non-analyticity. So this is the spontaneous, like the Higgs mechanism in the high energy theory. This works just like this. You have this symmetry, like the Hamiltonian has a symmetry, but the vacuum doesn't have that symmetry, so there's a spontaneous symmetry breaking. This is just like that. The Hamiltonian has a symmetry, but the free energy, which is like the vacuum, doesn't have that symmetry, so there's symmetry breaking. So this is in a sense like Higgs mechanism. Anyway, but if you do this, like if you go like this arrow, then that gives you a continuous phase transition. And we will show later that at continuous phase transitions, you need conformal field theories to explain the phenomena. Okay. And on contrast, if you move like this, like from left to right, here, this was the minimum. Like I'm changing h actually. A is less than 0. I am changing h from negative value to positive value, right? So it moves like this, come to this point. At h is equal to 0, there are two minima. It jumps to this minima. Okay. So if you move like this, then there is so-called first order phase transition. Well, why first order? Because the first derivative of free energy has a discontinuity. You see this thing. Because this was the minima, right? This is the x value is the value of m, which is the first derivative of free energy actually. It's like negative. So moving like this is like moving like this here. So it's negative comes here, here, here. At h is equal to 0, there are two minima, like here and here. And if I keep changing h, it jumps from this one to this one here. So it goes like this and then jumps here. So there is a first order phase transition. If you change h at constant negative a. And the earlier one, this continuous phase transition, you can see it here. The free energy and the first derivative are continuous, but there is an analytic. You can see it here. There's a cusp here. It's not analytic. You see? You cannot take derivative at this point, for example. But the first derivative itself is continuous, so we say it's a continuous phase transition. Are there any questions so far about what's a continuous phase transition and what's a first order phase transition? Okay, So if I were to plot this down, let's say, let this be, actually, let me, okay, okay, let this be A, okay, let this be A, and you know what, let me draw it like this. So, yeah, okay, no, never mind. Let this be A, let this be H. So if H is 0 and A, sorry, if A is negative, then there's a phase transition like this guy here. So as I move like this, I go from one phase to the other phase, from one minimum to the other minimum of the symmetry. Okay, so there's this blue line which denotes a phase transition. And at the end of that blue line, here, the end of that blue line, when H is equal to 0, but I change A from positive to negative, like if I go like this, then at A is equal to 0, there's a continuous phase transition because, as I showed you earlier, at this point, there's a continuous phase transition here. So that means the end of first order phase transition at critical point is a continuous phase transition. Now, if we go back, okay, I went too back. If we go back here, actually, this is exactly what we have. Through this line, we have a first order phase transition. At the end of this line, we have a continuous phase transition. So we expect the critical point here to be explained by a conformal field theory. Okay, good. So let's see, what time is it? Okay, I have half an hour left, right? Good. All right, so that was a nice motivation in the Lambda formalism. I'm just gonna gloss over details. Please see my notes. I try to write them as pedagogical as possible. I could. Okay, so then we can ask this question. Okay, sure. We saw that there's a continuous phase transition at uniaxial magnets, but why is it important? Like, why should I care? After all, uniaxial magnets are an idealization, right? We don't have uniaxial magnets around us. If we have magnets, they like a magnetization in 3 dimensions, not in 1 dimension. But here is the thing. There is something called universality, and it's extremely important. And it goes as follows. If we have some critical phenomena for some theory, let's say the uniaxial magnets, and if you understand that behavior there, if you understand the mathematics there, how things are, how the heat capacity behaves, how susceptibility behaves, etc., then it explains not only uniaxial magnets, but anything in the same universality class. So in other words, the CFTs, oops, sorry, my bad. The CFTs are divided into universality classes. Okay, universality classes. And the same CFT explains both fluids at their critical point, and uniaxial magnets at their critical point. So if you understand the CFT for the uniaxial magnets, you can use the same CFT to explain the behavior of water or carbon dioxide or nickel magnets, like whatever. So there are many different things in the same universality class that you can use to explain if you understand the CFT. Like, I want to go forward to show this actually. Just give me a second. That was like this nice. Okay, so for instance, so this list, this 5 list here, these things here, these are just, this is a sub list, by the way. These are all explained by the same CFT. It's called 3D Ising CFT, and this is called 3D Ising universality class. Okay, but these are all with the same CFT. So if you want to understand some polymer solutions, or if you want to understand the idealized nickel, or like liquid vapor transition, like process of aggregation of certain surfactant molecules, like some electrodes, whatever. There are lots of different things, like in chemistry, in solid state physics, in by the way, in QFT as well, because the same CFT also explains Wilson-Fisher fixed points, which is related to scalar fields in quantum field theory. So it's the same CFT that explains all of that. Okay, this is the concept of universality, which is why I started my explanation with statistical physics. Like you may be wondering why I start with the fluids or phase transitions, because I was trying to motivate it. If you understand that CFT, you can use the same CFT everywhere, basically. Okay. Of course, this is not the only CFT, only universality class. There are different universality classes as well. They explain different phenomena. But the thing is, there are like maybe hundreds of possible cases, but only a handful of universality classes. So understanding one CFT is really, really useful in that sense. Which is why uniaxial magnets are so useful, because they are simple to work with, right? But that CFT can be used in many places. Okay, so we went through this. We said that there's this universality, which is good. And we can then ask, let me just go a little bit more about this critical phenomena. We can then ask, okay, we said the second order phase transition or the continuous phase transition at the critical point, the end of that first transition line is explained by CFT, okay. But what happens there? Like, do we have any empirical things going on? Like, do we observe anything unusual? Well, yes, thanks for asking. Oops, what? Sorry, my bad, where is it? Okay, good. So we have this thing called critical opalescence. Okay, so this is like atom at constant volume. Okay, so we pass it to its critical point, like that point, this point. Okay, we are passing it through this point, and we see that at that point it becomes opaque. So you can no longer see through it. Now, this is not a property of atom. You can try this with many things like carbon dioxide, water, methane, propane, I don't know, like ethanol, like many things. They all show this behavior. Like basically any fluid shows this behavior. If you have any fluid, go to this critical point, they become opaque. Now, we can ask why. Actually, this is like one of the oldest things that people are like in this area, of course, in the CFT. Like they started being interested in CFTs because of this observation basically. Physically, what happens is that at the critical point, the fluctuations become scale invariant, which is scale invariance is like a subsymmetry of conformal symmetry. So the fluctuations become scale invariant, meaning that we have fluctuations at all scales. So all different frequencies of light are getting scattered. Okay, like at ordinary times, some frequencies are scattered. Like if you just send some light to the material, some frequencies are observed, some frequencies are scattered, some of them just goes through it, right? But at the critical point, the behavior becomes scale invariant and all frequencies are scattered. So the material becomes opaque, which is actually a firm indication that there is scale invariance at this point. Okay, are there any questions so far, by the way?
Can I ask a question?
Please.
I had briefly read over notes as well. I wonder if there's an equivalent phenomenon to critical opalescence in uniaxial magnets, for example, i.e. another item we studied on the same universality class.
Actually, I have a very good video. Okay, let's see if I can find. Oh, you know what? I can put it in the Slack channel. So
okay.
With uniaxial, what happens is like this. Okay, not something like this empirical, but you can see it in simulations. And what I had was like a video of a simulation with uniaxial magnets. Okay, so if you're away from critical point, like it either gets ordered or disordered, right? So if you zoom out from the magnets, like let's say you look with the microscope and you zoom out slowly, then you either see an ordered phase, all the spins are pointing in the same direction, or disordered phase, like they're random. Okay, but at the critical point, it is not neither ordered nor disordered. It becomes scale invariant, so you see this weird behavior that same structures appear over and over again when you zoom out. Just like this Mendelssohn bread. I don't know how to say it. You know, this, okay, never mind. It says it can scale invariant, so you observe this behavior. I can share the video in Slack channel.
Thank you. I'll be looking forward to that. Thank you.
Okay, great. Let's see. So that was the motivation. So that's good. And how do we see this mathematically? Well, okay, let me be brief here, but basically, let's say I have this point here, x, and I have some fluid with the density phi x. Okay, so phi x, let's call it the water, okay? And phi x is density of fluid at one point x. And this is point y, okay? Now, the density at point x and density at point y should be close to each other if x is close to y, right? Because we are looking at equilibrium values. So if you were looking at non-equilibrium values, they may be different. Like maybe a ripple has passed, maybe like there is time-dependent effects here, something has happened, whatever. But if you look at equilibrium values, if x and y are very close to each other, you expect the densities to be close to each other as well, right? So this is the correlation function of that, how densities correlate with distance. And it takes its general form. And this is by the two-in quantum field theory as well. It's just two-point function of a massless scalar. Like, for example, the two-point function of Higgs. You can write like, oh, you cover interaction. So this is like a general thing. Okay, so we have this correlation function of density of water at point x and point y, right? And it goes like this. It has a general formula. Details are not important. The parameter psi here is called correlation length. Okay, so it basically says how far this interaction goes. Now, if correlation length, this psi, is infinite, then this correlation never dies out. It goes like x minus y to some power, let's say 1 over x minus y squared. Okay, it goes to 0, but it doesn't vanish exponentially. It vanishes as a power law. So this is called a long-range interaction. Okay, let me rephrase myself. So this psi is the correlation length. Okay, if psi is finite, then exponentially suppressed. So it's a short-range interaction. But if psi is infinite, then it's a power law suppressed, and it's a long-range interaction. In quantum field theory, that would mean if psi is infinite, you have a massless field. And if you have a massless field, you have a long-range interaction. Like, for example, quantum electrodynamics. You have photon is massless. In statistical negative terms, psi is infinite. So it has an infinite range of interaction. On contrary, like weak interactions like are mediated by the bosons W and Z, they have mass, like W has a mass, Z has a mass. So the weak interaction is a short-range interaction because it's exponentially suppressed. Okay, because psi is finite. So anything I say in statistical mechanics has a correspondence in quantum field theory, by the way. So, but we see that at the critical point, psi becomes infinite. So at the critical point, we get massless excitations, which is why we have scale invariance, which is why we will get conformal invariance, which is why we can use conformal theory to explain critical phenomena or what happens at that point, like critical operations. Is this clear? Are there any questions so far?
Hocam, can you repeat the very last part about the massless excitations?
Sure. So what I was saying is that this psi is the correlation length, right? In the statistical mechanics. And if I was writing if I was working with quantum field theory, I would instead consider particles with some masses, right? And psi roughly goes like n to the minus 1. Okay, the inverse mass. So if psi is finite, that means this psi is associated with a massive particle in QFT language. Okay, so there's a massive particle, and that means there's a finite psi, and that means the interaction is exponentially suppressed because this term, actually, let me just clear this. because there is this term, this is exponential. The interaction is exponentially suppressed. It's called short-range interaction. On the other hand, if psi was infinite, that would mean this phi field would be associated with a massless particle, and the interaction would be power law. Like this term would drop out if psi is infinite. And we call them long-range interactions. Okay.
Yeah, actually, I didn't understand the part of this classification, but I couldn't clearly hear the part where we talked about the scale invariance thing at the very end.
Oh.
Can you a little elaborate on that if you have time?
Okay, so well, I will just say this: if you have a mass, it's a very intuitive argument. If you have a massive particle, okay, let's say I have a massive particle with mass 100 GeV. Okay, so and I can write this GeV in terms of, let's say, some length. I don't know, 1 nanometer or whatever. Okay, so that means if I have a massive particle that introduces a mass scale. So whether if I change the scales, if I call 1 centimeter 1 millimeter now, then the mass of the particle will be different. So I don't have scale invariance. If I had scale invariance, I would be able to change, 1 centimeter to 1 millimeter, but basically nothing would be different because nothing depends on the scale. Like
thank you very much. Yeah,
okay.
Thank you very much.
Sure, no problem. Okay, so yeah, I'll just go over these details. So in summary, okay, let me just go over summary quickly. So matter has different phases. Sure, we know this. And all phases can be shown in n-dimensional diagram, phase diagram. And phase diagrams have non-analycities, right? And these non-analycities, include phase transitions, which end at critical points. And we saw that these phase transitions are usually first order phase transition. They don't have to be, by the way. What I just showed was a lambda formalism, which is not valid everywhere, but it was just to motivate you guys. So most of the time they are first order phase transitions, and at the end of those, we have the continuous phase transitions because of the spontaneous symmetry breaking. Okay, again, this doesn't have to be the case, but that was one example, which is true in these cases. Okay, I'll just go over this. And for example, this is like for helium-4. It has this line which has continuous phase transition. So even though this is a line, this is not first order, but continuous phase transition through all lines. So there are examples like this as well. It doesn't have to be what I described. Okay, and we say at these critical points, we have scale invariance, which actually would lead to conformal invariance. Now I think I have 15 minutes, right? Yeah, I have 15 minutes.
Before you go into that,
yeah.
So in the previous example of the helium-4, so it's more like a critical line than a critical point, right?
Yeah, this is a critical line, exactly. This is called Landau line. It's a critical line. So we have critical surfaces. They can be of n dimension. They can be point, line, 2-dimensional, whatever. So in the case of fluids, it's just a line. In the case of helium-4, so in the case of fluids, most fluids like ethane or water or carbon dioxide, it's just a point. In the case of helium, it's a line. I don't remember if there was an example for higher dimensions, but yeah, they don't have to be specific dimension. Okay. So actually here, I will skip this. So in this section, I describe renormalization group formalism. I review it. I would highly suggest that if you don't know the subject, please go through it because it's a very basic review, but I think you may find it quite useful. I tried to write it introduction. I will skip this. And so earlier I was talking about this Wilson-Fisher fixed point. Again, like this is the same thing. This is used for quantum field theories with scalar particle. So if you start down, there's that fixed points, and there is this line. It's like the critical line, and it's like the phase transition critical line. And at the end here, we have the continuous phase transition because this is described by a CFT. And it's the same CFT, by the way, that describe uniaxial magnets and water. Okay, it's the same CFT. Okay. Okay, I skip RG flow, I skip this, blah, blah, blah. So I want to quickly review these points because I think they're important. I really think they're important because when I was taking the courses, no one really told me this. I think this should be told in even undergrad. Okay, so first thing, strongly coupled quantum field theories or statistical models are not solvable. I mean, we don't know how to solve them. And this is a very basic thing, but I think we need to stress this. These are not solvable things. We don't know how to solve them. We don't have the mathematical formalism for them. As I said earlier, not only we don't have the required tools to solve them, but also we may never be able to find the formalism to solve them. Because as I said, in some cases, they are proven to be undecidable. Okay, so we don't know how to solve them and we may never be able to. If we stuck with the microscopic Hamiltonian, like if you insist I will use microscopic Hamiltonian and do this, you may never be able to do that. Okay, now, if we cannot solve them, what can we do? If we can solve them analytically. Like the first thing you can do is put them on a lattice, right? And simulate that in a computer. Now, this is called lattice simulations. It's a very common thing. Just put your theory in a computer, discretize it. You need to discretize it to be able to put it in a computer. Maybe this field may change with the quantum computers or analog computers, I don't know, but currently you discretize it, put it in the computer and evaluate it. Well, it's good, it is a relative success, but it's limited because computer power is limited. Like you cannot have millions of lattice sites simulated. And also the complexity of this problem can be rather high. For example, I was talking about this CFT to explain the Wilson-Fisher point or water or uniaxial magnets. That same CFT is proven to be not really solvable on lattice. Like it's recent, it's 2000. I mean, when I say recent, last decades. So it was shown that solving 3D Ising model on a lattice is an NP complete problem. So if you don't know, this basically means it's very hard to do that. Okay, it's in a computation sense. Okay, but you can try that. Lattice simulations. What else? Now, we know how to solve three theories. That's good. But we cannot solve strongly coupled theories. We may assume that the coupling is weak, right? Just assume that it's a weakly coupled theory. It's almost free, and do perturbation theory. This is basically what we do for standard model. Like most of standard model just uses this. We assume the theory coupling is weak and do perturbation theory around free theories. Like when you do perturbation theory, you basically use free fields. Look, this is the Gaussian approximation in the pattern table. Okay, so the thing is, luckily, the fine structure constant, the relative constant, the coupling constant for electrodynamics is really small. So this theory really works for QED. It works also for weak theories. For QCD, not really, like if you're high energy. But you can always find some regime where this works, but it's not really a good solution. It's a fine solution to get some results, but not the ultimate solution. Also, some effects are non-perturbative, so you cannot access everything by this approach. Okay, that's also another reminder. Now, if we cannot take the coupling constant to be small, we can vary different things. Let's say we have a scalar field, phi x, it's strongly coupled. We can assume there are n copies of it, okay? And most of the time, if n is infinite, the theory is actually infinite. So we expand this around n. So basically, instead of working with phi x, instead of working with this, work with phi ix. I goes 1 to n. And as n goes to infinity, this becomes a free theory. This becomes a free theory. So you expand around n is equal to infinity, right? So you get the results for phi x by like 1 over n expansion, something, 1 over n squared something, 1 over n cubed something, blah, blah, blah. This is called n expansion, large n expansion. And like there's a huge, like people use this all the time. There's a huge literature for this. I also like attached the review. Another thing what we can do is so-called Epsilon expansion. Now, for some cases, the theory is free at a specific dimension, but not at other dimensions. For instance, we have been talking about this 3D easing model, right? That critical point, that Wilson-Fisher model that explains water, etc., etc. Now, the thing is, the critical point at which the CFD lives at a critical point, the Wilson-Fisher fixed point, this one. Now, and this is the free theory, Gaussian fixed point. So this is the what we want, and this is free theory, what we know how to solve. Now, this what we want, this critical point, approaches this free theory as d goes to 4. In fact, at d is equal to 4, they are same, that they coincide. So what we can do is we say, oh, okay, let the space-time dimension be 4 minus epsilon. Epsilon is small. Now it's almost free. Do expansion with epsilon, and then later take epsilon to 1. So we take epsilon is equal to d minus 4, assume it's small, do expansion, at the very end take epsilon to 1. This is called epsilon expansion. It's also very commonly used. And most of, there are lots of computations done with this way, because some results, this critical behavior was computed this way. But the thing is, again, this is like a asymptotic expansion. There are very many mathematical methods to improve them. There's so-called Borel summation that improves this computation. But at the end of the day, it's an asymptotic expansion, so you really don't know what you're doing, honestly. Okay, so this is the picture. The reason I'm saying this is that we really don't know how to solve a couple of theories. But if we have conformal symmetry, then we have a very well-established way of constraining these theories, which is why relying on conformal symmetry or using it whenever we get the chance is very important. Like supersymmetry is like that as well. If you have a supersymmetry somewhere, you should use that. Because most of the time, we really cannot solve anything. But if you have some additional symmetry, you should use it. And we do get the conformal symmetry in many ways. Now, in my last minutes, let me just focus on, okay, I'm just gonna skip this. Here, I talk about scale invariance, dimensional counting, some classification operators. Maybe I can go through them tomorrow. I can review them tomorrow again. After all, I think these are important points. But let me just finish with something. Maybe talk about this, what we are using CFDs for. So, okay. So as I said, okay, using CFDs beyond statistical physics. Let me just finish with this today. Tomorrow we can go back and review some of the details. So as I said, okay, the 3D easing model, the one which is famously hard to solve, this MP complete problem that we can solve on lattice, etc. This thing explains many phenomena, we said. But there are other universality classes like XY universality class, Heisenberg universality class, and there is some other stuff. Okay, not really important. I put some references. Now, apart from those, we do have CFDs in many places. Some examples are flat space holography, string theory, quantum field theory in general, ADS-CFD correspondence, and cosmology. These are some examples. Now, the first two items are basically 2D CFDs. So string theory, Gökhan has already explained them, so no point talking about this. This thing, flat space holography, is relatively recent. There was a 2016 paper by Strominger. I put some reference here if you're interested. It basically says that scattering amplitudes in 4-dimensional flat spacetime can be related to the CFDs living on null infinity of Minkowski space. So basically, there's a correspondence between 4D scattering amplitudes and 2D CFD correlation functions living on the null infinity of Minkowski space. An interesting topic, but we won't be caring about this in these talks. Yeah, I actually wrote a paper in this topic. I tried to put in my opinion, pedagogical introduction to that, so you may want to check it. I don't want to like do my own marketing, but I think it was introductory. Okay, so when we say quantum field theory, oops, oh, sorry. Okay, oops. Yeah, it should be some, okay, there we go. So when we say quantum field theory, I mean as follow. So take any quantum field theory, okay? You can draw a phase diagram for any QFT, and that QFT under RG transformation, which I didn't review today, but it's in my notes, and maybe we do it tomorrow. That QFT changes its coupling constants, those phenomenological constants I talked about earlier, like compressibility or viscosity. All QFTs have such coefficients. They change those interaction coefficients, and they change such that the QFT flow to a fixed point at IR or at UV. Yeah, I mean, at very high energies or at very low energies, the QFT goes to either a scale invariant theory. Most of the time it goes to a CFT. Okay, it doesn't have to be CFT, but most of the time it goes to a CFT. I explain other cases here. And so, even if we are not at very high energies or at very low energies, we may be around the CFT. Okay, we may be close to a fixed point. So we have this so-called walking behavior. Now the coupling constants are called running, like they change. Maybe you heard this, like running coupling constant for QED, etc. So if they're close to a fixed point, they are called walking, and that can be used to explain many phenomena, like some beyond standard model phenomenology, or like weakly first order transition systems mechanics, etc. So they are really used in many fields. Okay. Also, gauge theories are expected to have conformal windows. Okay. What this means is that if you have a gauge theory, let's say you have a gauge group, let's say it's like QCD or QED. Like we know that all standard model fields are gauge, like it's the backbone of standard model. If I have, let's say, some SUN theory, SUN gauge field, SUN color. This is like its color. It's SU1, it's actually, sorry, U1 for QED, SU3 for QCD, etc. And let's say I have n number of flavors. So I have SU and F number of flavors. Like, for example, how many quarks I have? Like I have bottom quark, top quark, you know, charm quark, strange quark, like the flavors of quarks, for example, like how many quarks I have. Okay. So NF is like number of flavors, and C is number of colors, how many gluons I have. So depending on this relation, the theory may be conformal. Okay. So this X is like ratio of NF over NC, number of flavor over number of colors. So number of quarks versus number of gluons, roughly like that. So depending on this number, the QCD or any gauge theory may behave conformal. So this is called conformal window. If NF is too low, we get the symmetry breaking, chiral symmetry breaking. If NF is too large, the theory is asymptotic, Linat free. But at just some window, it's both asymptotically free and it's not chiral. There is no chiral symmetry breaking, because if there's chiral symmetry breaking, that generates mass scale. Here, not asymptotically free, but at this range, it's conformal. So all gauge theories do have some kind of conformal, not all of them, but many of them have conformal window. Okay, so I don't have, actually my time is finished, but I just want to use 2-3 minutes from your break, coffee break, sorry. Like for example, this is the phase diagram for QCD, by the way. As I said, like, you know, you remember the phase diagram for fluids, right? It goes like this, there is this, right? Like gas, solid, liquid, this was pressure, this was temperature, you remember it? It's just like this. This is for QCD. Oh, this is schematic, but I have baryon chemical potential here, temperature here, and there's a critical point here in the phase of QCD, which is described by CFD. Okay. And there is ADS-CFD correspondence I already mentioned. And lastly, let me just briefly go over cosmology in 2 minutes. So If we accept cosmological principle, which says the universe is almost isotropic and homogeneous at very large scales, which is, by the way, may not be true. I also put this footnote, there's some discussion here. If we accept that, then we can use FLRW metric for it, the FLRW metric. Then we define the Hubble parameter, HT, like this. Here, AT is the expansion parameter, okay, and T is time. Now, we can show that, long story short, this, if we take Hubble parameter to be approximately constant, that leads to DS metric, de Sitter metric, okay? And we know such errors, like if we have inflationary expansion, during inflation, there are some times where Hubble parameter is almost constant. And during those times, the metric is almost de Sitter. And it has exactly a CFT isometry, which lives at its boundary. So we can use CFT isometries and CFT correlation functions to extract correlation functions of cosmology, like non-Gaussianities, etc. So CFTs are useful here too. Okay, I think this is good enough. I think I will go back and review RG formalism tomorrow, which may be quite helpful. And that should be enough for today. Are there any questions? I see there's something on chat. Please do not use chat. Please ask, just unmute yourself and ask. I don't know, because I cannot track the chat in the meantime. Again, there's another thing in chat. Question limit in the sense of safety. Correlation that terms. Okay, so here is the thing. If you're working with, the question is, if you didn't see, is there any relation between correlation length and thermodynamic limits in the sense of CFT? Not exactly. Here's why. We need thermodynamic limits all the time to get those non-analysities. Because if you go back to very beginning, let's see, let me just go back to very beginning. And okay, where is it? It's right here. So if you remember, we have this expression, right? Sorry. We have this expression. Here's the problem. Hamiltonian is analytic function, analytic. And F, the free energy, needs to be non-analytic to have phases, phase transits, etc., to get the CFT. It needs to be non-analytic. The only way we can get a non-analytic function by summing analytic functions is if the sum is infinite. So this trace needs to be infinite, And this is precisely thermodynamic limits. So I always get phases, phase transitions, that safety description, etc., only after thermodynamic limits. Okay, so I need thermodynamic limit all the time. I'm not sure whether this answers your question, but that's the way it's related. Is there another question? Okay, so since the time is limited, I have to be quick. Please ask me any questions in the Slack channel. There's also discussion today at what? At 3:30, right? So there's a free discussion time. You can ask then as well. And I'll see you tomorrow. We will continue tomorrow. Okay. Oh, by the way, it's not finished. I said I see you tomorrow. The summer school continues. Now we have a coffee break. And we will begin in 10 minutes. Okay, so please be back in 10 minutes. you.